All right, welcome everybody. Thank you for coming. It's a pleasure to have here today Dr. Anna Scaglione from Arizona State University. Dr. Scaglione is a professor in electrical engineering at ASU. She's been there since 2015, and she was, prior to that, she was a professor at UC Davis. She was also at Cornell and University of New Mexico. She's been moving a lot. Dr. Scaglione is very prolific, but in sort of basic, intrinsic expertise is in statistical signal processing with applications in communication and also in power systems. She knows more about power than actually power people. And as I said, her work is very broad and extends to modeling and data analysis for complex networks, information systems, sensor networks, and intelligent infrastructure in energy delivery, as well as social networks. She's an IEEE fellow, and she received the 2000 IEEE Signal Processing Transaction Best Paper Award, and was the 2013 IEEE Don Fink prize paper recipient for the best review paper in IEEE. Her work also got recognition by the IEEE Signal Processing Society as the best young author award for a paper. Without further ado, it's a pleasure to have her talk to us today about some of the work that she's been doing in social networks. And with that, thank you for coming.
Thank you so much.
And the floor is yours.
Thank you so much for having me. It's a little bit awkward. I will have to change the slides here if you see me touching. So I'm going to talk today about some work that I've done with obviously several collaborators and students. And the theme of my research is broadly sensing information. And at some point in my career, I found myself interested in social networks because I realized that learning problems that arise in engineering are very similar to learning mechanisms that model social influence. So what are opinion dynamics? Opinion dynamics are models, exactly mathematical models that try to capture how individuals influence others, okay? And the idea of using mathematical models is not that new. In fact, it was during the period of the French Revolution that a French Marquis, the Marquis de Condorcet, advocated voting as a better form of government because he had discovered, along with other statisticians, that if you add a lot of noisy measurements, you can actually essentially remove the effect of the noise and obtain a much more accurate estimate. So he saw a mathematical proof, essentially, that democracy was a better form than monarchy for government. This notion was actually popularized by a famous paper by Francis Galton at the beginning of the 18th century entitled Vox Populi. So that's really what has opened up the scientific approach in studying opinion dynamics. So what is the difference in a system of agents that are learning? Like, you could find easily this particular picture in a detection and estimation textbook. But in fact, it can capture also the mechanism in which agents learn. So there is a critical difference between making a decision based on your own information about the environment. And here, the information about the environment can be modeled by some sensor measurement S, which has a certain relationship, statistical relationship with this latent variable theta. And if you learn under social pressure, what you are exposed to is the actions that other agents make. And the actions that other agents make themselves are affected by the observation of other individuals' actions. So this principle is the principle that leads, this model is the model that justifies the idea of social learning. However, it doesn't always lead to the correct solution. It doesn't always lead to what the Marquis de Condorcet thought was the answer to the problem, which is essentially the optimum fusion of all the information that is available at the individual sites, which is what you would do if you had a sensor array. So my talk is going to be organized in 3 parts. A first part is really an introduction, a broad introduction to what are the most popular models for opinion dynamics in the literature. And I will say this is the analysis part. All of these models are theoretical models that try to capture trends. The second part is a part in which I try to postulate these models could, in essence, allow you to identify parameters that essentially explain social phenomena that are happening actually in social networks by observing data and fitting those data to that particular model. And that's really the holy grail of opinion dynamics models today. And then I'll show you an application of the theory behind this social network identification problem. And as the title of the talk clarifies, I'm interested in polarization in particular, because that's the interesting phenomenon that, that really reflects more how social behavior occurs. So occasionally we have social learning, but oftentimes we have dysfunction in society, and there are many behaviors that one can characterize, but broadly speaking, you can divide them in 2 types of classes. One is alignment of social behavior, so everybody happily going to throw themselves off the cliff. In economics, after these first studies by Galton, in fact, there were many other studies that were suggested by experiments in psychology that led to the notion of groupthink, and economists try to characterize what would be the mathematical explanation for this herding behavior. But this goes under several names in different scientific communities. So this idea of fad and trend behavior has been studied by obviously social science and psychology, and in political science this will be the bandwagon effect. The other interesting class of models instead tries to capture the effect of disagreement, the fact that maybe isolated or groups split and their opinion remain polarized, and in a period of elections this is a particularly obvious phenomenon that we are all exposed to. And so social influence models in this case could be driven to this particular division because you have MSNBC and Fox News, which are sort of the mavens, the zealots that are trying to convince everybody else of certain opinion, or it could be actually the result of agents that are perfectly homogeneous. They are talking to each other, but eventually they have some intrinsic lack of trust for those that are too far in opinion compared to their own belief. So it's always great to come up with a very simple model to explain these phenomena, and in a way, in social science, the Groot was lucky because no one earlier had tried to find dynamics that were so simple in his particular field. And so he tried to find a very simple model to explain alignment, and the simplest model you can think of are obviously linear models, right? So that's how he came up. So let me introduce a little bit of notation. In the opinion dynamics model, typically the social system is described by the graph. V is the set of vertices, E is the set of edges, and this is a weighted graph. So I'm going to use this matrix W as the matrix of weights. Every edge has a specific weight. Now, the state of the agent is denoted by this variable x. I is the index of the agent. And here I have 2 indexes, because the interaction happen very frequently, and that's the interaction index is t. But they typically pertain a certain topic. So you have several conversations, for instance, about the election, and then you influence each other. Okay, and so let me assume that I have a state vector for the entire network of n agent, which is this vector. What did I do? And so in this case, the linear dynamical model says that this vector of states at time t minus 1 affects the vector of state at times t through this mixing matrix. This is a simple linear equation. So what is the state? The state is a belief. Typically, in the Groot model would be the probability that you take a binary action, yes or no. I go to the restaurant, I don't go to the restaurant. And this is how your opinion changes after a conversation or after having observed for a sufficient number of time others and having a sort of internalized probability that your friends will go there. The typical assumption in the Groot model is that this matrix of weights is a stochastic matrix. What does it represent? It could be the probability that you copy the action of the agent that you observe, and so therefore the sum of these probabilities equal 1. And the theorem, this theorem essentially proves a very simple fact of linear dynamics, that if this is a stochastic matrix, then, and if the network is connected, then the network will asymptotically converge to a state of consensus. All of them will agree, and what will be the state of consensus? The state of consensus here is due to the fact that this is the vector 1, so everyone will have the same opinion, right? And the opinion will be essentially a weighted combination of the initial opinions of all the agents. So this is just the inner product between some constants, which depend on the eigenvectors of this matrix, and the initial state of the agents. Now, if you give a different interpretation to X, it doesn't have to be necessarily a probability. If you, for instance, are using this dynamic to capture how the agents share their log likelihood functions on a certain parameter theta, then actually this becomes, in some cases, a perfect mechanism for social learning when C is precisely averaging these entries. And that happens also if you have the noisy measurements the Marquis de Condorcet was talking about. You have theta plus noise, you average, you obtain the same effect. So asymptotically, if you have many agents that do that, in these cases, you will actually have a good phenomenon. The alignment will be towards the correct answer. So that's essentially the situation. You interact several times. Initially, everybody starts with a different opinions. As t goes to infinity, the agents reach consensus, which is an average of all the initial measurement. Now, in practice, we don't observe, as I said, oftentimes a full agreement among social agents. So this model can be actually modified fairly easily to include the presence of mavens. This is actually the work that started me on this path, because these models of consensus are also used in signal processing and working to essentially describe the situation of a wireless sensor network where sensors have to coalesce their measurements for a good decision. And it was one of my students that sort of opened me up to this area of research, and he suggested to look into a case where you actually have some agents here that instead of averaging their beliefs, they're sort of stuck. These are the stubborn agents that don't change information. However, they interact with others, and others continue to exchange information. So in general, in these configurations, unless these nodes are coordinated and have exactly the same initial opinion, the network will not converge. If they are coordinated and have exactly the same opinions, they will drive the network to agree with them. Okay? And so that's the interesting phenomenon that one can capture just as simply as the other case. And in this case, what happens is if you group, what am I doing? If you group the stubborn agents all as being the first NS agents, I didn't touch it. If you group them to be in the first group, then basically what you have is that the trust matrix has a block, which is an identity matrix. There is no trust between the stubborn agents and the other agents. And the other two blocks have an important meaning. This is the block with which the stubborn agents are essentially influencing the other agent. They are essentially sending their signals as an input. And this is instead a matrix that represents the mutual trust between the agents themselves. And since there is going to be some weight here in general for the agents that are stubborn, this matrix is actually a substochastic matrix. So you can actually compute, again, under the assumption that all of the rows of this matrix add up to 1. So you can actually compute the steady state of this configuration and show what I said before in words, that the opinion of the normal agents will only depend on the initial opinion of the stubborn agents. They never change it, so it's going to be also the opinion at infinity, times a matrix. And this is how the network affects, in essence, the dynamics. And it's very simple to calculate that this is the result just by looking at the lower blocks as you raise this matrix to the power t. Okay, so we talked about a form of disagreement in the network, but disagreement can arise even if the agents act exactly in the same fashion. And there is another model that tried to see how people then become stubborn and polarized. And again, it's very simple dynamic. It's actually very interesting how these models that are so simple can capture this phenomena. So there are two versions of this model. One is called the HK model from Egselman and Krauss. They proposed it in 2002. Actually, predating that model is the model by Defuan, which is the one that I'm showing here, where the interaction, instead of being a systematic interaction among all agents, actually occurs at random. So let me denote by you the unit step. So the dynamics are simply here. So the agents that are communicating perform potentially a convex combination of their current state and the other state. And here in this case, the convex combination is really half. So they average exactly the two states. But the difference here is that this function here is a unit step. So if the distance here, the distance between the opinion of the agents is less than t, then this coefficient is 1. If the distance is greater than t, then this coefficient is 0. So they get stuck. They keep believing what they believed before. And what is interesting is that if you change this parameter, then if the threshold is very low, you observe that the opinions, these will be the opinions, the initial opinions of the agents, they converge, but they converge to two different values in this case. If you make it lower, it will also converge to a greater number of opinions. And instead, if the threshold is high enough, you actually converge to agreement. Okay? So here you have a convergence not to a unique state, but you, in essence, see multiple states. Now, you don't have to have always a single variable x. You can have a vector. So this could be, instead of a probability of a 0-1 event, it could be the probability mass function of multiple options. So here, for instance, you have three possible values for the decision of the agent. So you could be positive, negative, or neutral. And so the probability mass function will be lying on this simplex. And what these points represent is, in fact, the opinion of the agent. And you can see that even in this case, you see these dynamics that if the threshold is low, you see the opinion split. If the threshold is high enough, you see the opinion collapse. Okay? And so the work that I did in this area was trying to assess whether I could have a sort of constant that I could measure that would tell me which one of these would occur based on the threshold and based on these probabilities that these agents talk to each other. And this was nice work by my student that was able to prove that the necessary condition for the agents to converge to consensus is that the distance that they have at the beginning, averaged with the weights that represent here the probability that they talk, is below the threshold. If it is above the threshold, then you know that they will not converge to consensus. The model of these agents communicating at random is a little bit unnatural because we have limited time for communication. We have potentially an agenda when we communicate. So we try to capture this with a variation of this model to see whether, instead of going through a completely polarized state, we observe a different phenomenon in this case. And so we define a utility that defines the probability with which I communicate with a certain agent, and we assume that this probability was chosen by the agent based on a utility maximization, where the utility is defined as follows: is the probability of getting a certain reward minus cost, and then there is a natural force, which is sort of an external phenomenon that leads to the interaction of certain agents. And why was that interesting? Because this actually leads to more natural, more intuitive type of clustering. So in some cases you have consensus, in some cases you have splitting, but the splitting is not as pronounced. So you still have a distribution. They tend to be in clusters, but not necessarily collapse on each other opinion. So that sort of reflects a little bit more what seems to be natural. So let me go through other two models. So in the previous models, it's always assumed that you have this smooth estimate of the opinion of the other agent, and that their interactions essentially vary your opinion in a way that is smooth, because the quantity is some number which is a real number. But in some cases, what we are affected by are directly the actions of other agents. So there is a very simple model that captures this, which is the voter model. I'm not swayed by some smooth estimate of the belief of the other agent, but rather directly by the actions. This model was proposed by Clifford and Sudbury in '75, so nearly at the same time where de Groot was proposing his model. And again, here you have a social network which is a graph, but the graph is not weighted. You have a certain set of edges that define who is connected to whom. And the way the agent update is essentially by copying the vote of another agent. So agents are voting in this very silly way. They're just copying the vote at random of another agent in the neighborhood. But in fact, you can associate to this an underlying belief. Because this experiment, the experiment where I copy the vote, can be interpreted as forming a belief, which is the histogram of the actions that the other agents in my neighborhood performed, and then utilizing this belief as the probability of a Bernoulli random variable that gives me my vote. So it is a form of model which is similar to the de Groot model, except that now I'm forming an opinion which is the histogram of the other agent, and I have no self-influence. I have no self-confidence whatsoever in myself. I just reproduce what the others do. We studied also this model with one of my students, going from sort of this, the Groot model to the discrete model of the voters model in the presence of mavens. So mavens in this case, the zealots, are those that stick to their vote. They never change their vote. They don't copy anybody. And we actually were able to prove that you get, obviously you don't converge in that case because you keep changing your vote, but at least you converge to a stationary distribution. And we also noticed that the position of the agents, the stubborn agents in the network, makes a huge difference in the variance. So even though you can have the same exact expected probability of, for each agent of choosing an action or another, the average action, right, the average bias that you have in the network strongly varies if you have networks in certain configurations, stubborn nodes in certain configurations, and or in others. So for instance, this is a network where the nodes in the middle are not stubborn. These are the two stubborn nodes with opposing opinions. And here you see that the average of the opinion versus time is fairly well concentrated. Instead, with the second placement, where the stubborn nodes are here, you see that there is a huge switching between the opinions. And in this case, it's kind of intuitive why that happens, because here the stubborn agents talk to everybody. Here they only talk to these guys, and so these are proxies for their opinions. And so we try to look at the problem of placing them optimally for a given topology, and we found that actually this is a fairly easy problem to solve. You can solve it with a greedy algorithm, because the optimization can be formulated at what is called a submodular problem which has a greedy solution. The voter model is very similar to the models that have been raging in the economics literature around the late 80s and 90s. And one of the most celebrated models is the so-called BHW model. Don't make me pronounce all these names. You can read them. So in this model, this is very similar to the picture that I showed in my second slide. So there is an environment, and each agent has an observation S, which is its private information, and the observation has this statistic. In their model, theta is binary, and the observation is also binary, and a certain probability of matching exactly theta, right? So there is a certain probability of error in the observation. And what happens is that these agents operate in a sequence. So the first agent performs an action trying to essentially decide what theta is, because it gets a certain price if it's correct in deciding theta. And so in this case, he will be only utilizing its private information. So the best choice that he makes is that S1 is equal to theta. But obviously, the second, third, and fourth agents and so on are in a different position because they saw what the previous agents have decided. So the decision that they make incorporates their measurement. And the theory that they developed looked at human beings as potential rational agents. What will they do? They will try to make the choice that based on their private information and all the observation that they have minimizes the probability of error, which will be the maximum posterior probability. So we'll be maximizing the probability of theta given everything that the agent I has seen. So this will be the rational choice, which, by the way, economists have already proven is not the way human beings think. But the interesting thing for them was to notice that the groupthink behavior would arise even if every agent is making the best it can do with the information available. So eventually, agents herd. Like in the voting model, they randomly converge to a vote, which can be wrong, right? So there is no effect of perfect fusion of information in this environment, and this was counterintuitive because you would imagine that as you integrate more history, you eventually are becoming more and more cognizant. And in fact, what happens instead is that some errors end up overwhelming the sequence of decisions. So let me go to the second part of the problem. So now we have these nice models, and for many, many years, people have thought of these models as just simply giving you some idea of how societies behave without necessarily applying them directly to data. But, you know, I am a person that works on data, statistical signal processing, so for me, intrinsically, when I have a model, I want to utilize it to fit in a parametric form what happens with data. And so that leads to social signal processing, which is also what Professor Krim right now is very interested in. A lot of his students gave me interesting insights on what they are doing. So basically, we have a lot of data about what human actions are because they leave a digital trace on Facebook, Twitter, and so on. And there is a huge collection of databases. So what do we want to do with that? We want to learn the parameters of this model. Now, we have, in the Groot case, we have a linear model. So this is not too bad. As long as you can gather from data an estimate of these parameters over many topics and over many times, in principle, you can estimate this matrix delta, W. And that will give you essentially another way of forming a social graph that is based on what actions or words these agents are uttering instead of simply looking at the interactions or the topics they talk about. The problem is, though, that, remember, this is a belief. It's something that happens in the human brain. Right, so you don't have direct evidence of that. You only have evidence of actions. And moreover, you don't know exactly when this interaction occurs, right? So when is that I internalize this model and I change my opinion? And therefore, this is, you know, one of the pitfalls of this model, that there is this perfect synchronous update of beliefs, which cannot be observed in practice. Now, the idea that we had was instead, why don't we look at the steady state equation of this system? In the general case, when we have complete alignment, the steady state is not informative because you have consensus and there are any stochastic matrix which is connected will essentially lead to consensus, so it doesn't give you any information about the weights. But if instead you assume that there are stubborn agents in the system, because either they're there and you identify them, or you actually place them in the network, then they can work essentially as an excitation to the system, because what you see as opinions of all the agents, all the actions of other agents, is in fact sort of the reverberation of what input the stubborn agents are putting in this system. So I made the analogy with a social radar. What you do in radar is you shine a signal and you get back scattering. So you can look at the opinions of the agents that are not stubborn as back scattering. And in this case, if you have sufficient number of stubborn agents and you collect their opinion over several topics, you can try to say, well, in all of these topics, the network is essentially at the steady state once I estimate the opinion, or is an approximation of that, and you can use these equations to estimate the state. So you can pose this model, and you need several assumptions to regularize this problem, because typically you will not have a majority of stubborn agents. And so we made some assumptions in formulating this problem. Everybody likes to deal with sparsity regularization, so we assume that social interactions are close only with the relatively few agents, so the matrix D of trust between the non-stubborn agents is sparse. And B, recall, is this matrix that establishes the influence of the stubborn agents. And we assume we have an idea of the support of B. We have an idea of who the stubborn agents are talking to. So eventually, this matrix could be having a lot of entries that are 0 also among the coefficients that we have to estimate, but we assume that the stubborn agents, since we have identified them, are traced with greater accuracy, and we know they don't talk to certain individuals. So we pose this problem, and then we try to understand whether this problem can be solved and has a unique solution. So we were able to understand, to provide a bound for how many stubborn agents you will need given a certain random graph for the social network that has a certain probability of connectivity. And so we saw that it's going to be always growing, unfortunately, in the order of the non-stubborn agents that are in the network. But luckily, if the system is sparse enough, so if P is small, this number also decreases. And in fact, since PE times n is the average degree of the network, in essence, we need a number of stubborn agents which roughly goes, safely could be chosen to be the maximum degree of the network. And these are the results for the mean square error that we have in the estimate of the entries of the matrix D and B. This is instead the support recovery, the number of errors that we make in these entries. Remember that there are n square entries in the matrix that we have to identify. Here we have the number of stubborn agents that ranges from 10 to 50. And here we have two different performances. So the blue is for the estimate of the matrix D. The red is the estimate of the matrix B. And the dotted line, the circles and squares, are with a random selection of stubborn agents. Instead, the solid line with the stars and triangles are with an optimum selection of the locations of the stubborn agents. So if you optimize the location of the stubborn agents, you have a very steep decline in the mean square error. This we are at 10 to the minus 4, roughly at 34 stubborn agents, and same with the support recovery. We need roughly 30 to be almost certain of all the connections. But as you can see, the speed at which it decreases is a function of, a relatively quick function after a certain threshold, and is not so great before a certain threshold. So in this case, this is not particularly exciting. We need 34 stubborn agents for near perfect reconstruction, which is not little for this size network. However, even if you don't grasp, it's kind of pessimistic to look at all of these numbers and these errors together, because you can see that if we have a much larger graph, this is a particular graph, it's a Facebook graph, which has 666 nodes, and you can see that the reconstruction algorithm does a pretty good job at identifying the communities that seem to exist in this network. And so the structure of the network is essentially preserved. Okay, so now I'm at part 3. How much time do we have? Okay, so I can go quickly through this. So so far I have talked to you on how to identify what are the guarantees that you can give with this method. So we try to apply this method to real data, and we wanted simple real data that contained actions that were simple to identify. So why not looking at US Congress and voting records, because they exactly has the kind of simple information to process. Because otherwise, if you process Facebook or Twitter data, you will have to essentially convert the text into an opinion or a belief, and that's a process which is slightly more complicated and heuristic. So in this case, what data set do we have? We have the content of different bills, so we can sort of classify the bills in different categories. And we have the voting result, and we also know the ideology, and we actually can score to a certain extent the ideology. And we utilize actually practically a leadership score as an indication of how stubborn these agents were. So we identify the stubborn agents based on this leadership score. And so the idea is to apply exactly the estimation method that we proposed before on this real data. So there are 100 senators here. There are 2 independent senators, and the remaining are Republican or Democrats. The bills are typically sponsored by a group of members, and the senators vote for the approval or disapproval of the bill. So this is the model that you saw before, but obviously we don't anticipate reality really fits this model. So what we assume is that this matrix is in fact changing randomly, but it has an average which is stable, right? So it's a noisy version of this W bar matrix that we were considering before. Okay, and in this case, obviously, Democrats, independent, these are all different agents, and so what we are interested in is in the relative influence. So the matrix is essentially blocked in several parts, and the top part will contain the stubborn Republican and stubborn Democrats, and the bottom part is also partitioned for the influence between the stubborn and non-stubborn agents, and we assume that the independents are not stubborn by definition in this case. So we collected the votes of Democrats, Republicans, stubborn and non-stubborn, and we did the fitting according to the model that I explained before, which is exactly the same, except that obviously there is noise in the model, but the equations that you can use to fit is the same. So what are the topics? We said that x of t, k is the topic. So we divided the bills in certain topics and obtained for them the voting record, and we calculated the belief as the probability of making a yes decision, and we averaged, we utilized not voting event as some kind of neutral state, so they contribute equally to the yes or no vote. So now at this point we have a vector that contains the steady state opinion according to our model of these agents, and it's split in two parts, and we can do the fitting that I was talking before. This is just a little detail on how these ideology grades are computed. In the interest of time, I'll skip that slide, but it was used essentially to identify the stubborn agents. And then we do our regression problem exactly in the way I described before, where, however, we utilize the partition that I mentioned before. And that's what we get. We can utilize different regularization. In this case, as I said, there is an ambiguity in this estimate, so we can choose the diagonal of this matrix in a way arbitrarily. And depending on that, you do get a different measure of the weight because you only know relative weight, but the structure, as you can see, according to the theory, remains very similar. It's just that you highlight certain influence rather than not. And so if you regularize it saying that the diagonal of D is 0, you are saying that the people that are non-stubborn have zero self-trust, but they also have a leadership score, so you could regularize it utilizing their leadership score. And then, again, as I said, you obtain roughly the same support but different weights. Okay? And the bright pixels that are in this portion essentially are the Democrats that agree more with Republicans or the Republicans that agree more with Democrats. So that part is the interesting part. And so obviously here we have different weights, so we can see, relatively speaking, how many of these senators, how much these senators trust these other senators. And if you know that, essentially you can decide to lobby only one of them instead of lobbying all of them, right? Because they will vote, they will be aligned. This was actually interesting. We saw that the trust of Senator Marco Rubio was actually fairly high for Ted Cruz. It didn't seem the case during the primaries, and that Senator Marco Rubio is fairly well liked. He has actually quite a bit of influence on others. Ted Cruz appeared not to have a lot of influence on many people, but actually quite the trust towards Senator Rubio seems to be fairly well reciprocated. So here are other factoids about, for instance, Bernie Sanders that seem to have influenced quite a few senators, and this could be skewed because Bernie Sanders was in a was promoting a veterans bill, so that was kind of a bipartisan issue. So you can see that this is picked up by this analysis. So we actually try to characterize, utilize the sum of the weights or the support of the weights to define impact or influence. So the impact factor is the L0 norm of the weights, so it's how many people you influence, and instead the influence factor is just the L1 norm, the sum of the weights. And one of the interesting findings here is a set of impact. So for instance, David Perdue, which I don't know if you know, it's a Republican from Georgia, has a lot of people he influenced. But if you look at the influence factor, Tim Kaine, which is the vice presidential candidate, is like right now 1.9 in influence factor. So maybe this was a reason why Hillary Clinton chose him, because he can help with bipartisan issues. We also noticed that if we aggregate women, they roughly have the same influence as men, which was kind of nice. And then we also looked at the influence between states, so we clustered senators based on state, and we were able to obtain, again, a difference influence matrix. And here we looked at states that had a leadership score that was high to identify the stubborn agents. And so, for instance, Texas is considered a stubborn state, and looked at the different influence factors for other states. And with this, I want to wrap up because maybe there are some questions. So I gave you an overview of several interesting models, and I think right now what is exciting is to try to apply this model and convert real data in the parameters, in the variables that are in this model, and extract information about the influence. First for insight, because you want to gain a different insight, right? We have a lot of data about social graphs, but they simply are measuring how many times people respond to each other. They don't look at the semantics of what they say to each other or their actions. And so this mechanism could be good ways of obtaining another way of weighting the edges that exist among those graphs. And then the next step is to be able to predict trends or optimize, do social engineering, and in essence utilize what you learn about the network to influence it, hopefully for good reasons and good objectives. Okay, thank you.
We have time for some questions.
So it seems interesting that the location of the stubborn agents matters in, the...
It does, actually.
Yeah.
That's a very good question. And it does affect your result, right? So the identification it becomes a little bit cumbersome because it's a combinatorial problem, like who are the best candidates to be stubborn agents given that I want to minimize this error in fitting my data. So that's a little bit an obstacle in sort of scaling this system. But one of the ways you could utilize is you place avatars. I mean, you place synthetic stubborn agents, or you are a lobbyist, you know their function, right? And you know that they are paid or they have a self-interest in injecting that particular opinion for economic reasons. So in that case, the identification is much simpler. And again, you don't have to identify them all. You have to have enough identified correctly to get the result that is correct. Because the remaining ones, if they are isolated, they would emerge from the estimate of the parameters. But very good question.
I have a couple of questions. So in your model, or models, I should say, it appeared to me that you always took, in other words, different discussions or different interactions did not influence one another.
Yeah, I'm assuming that the trust on average is the same. But those are evidence of different interactions. So the interaction is on a different topic. So I don't know that they have to be completely uncorrelated topic. And that's why I think using the steady state equation is a little bit more robust. So I'm saying these networks model have exponential convergence. So I'm pretty soon reaching their steady state, right? So I can say that pretty soon what I see is a perturbation of the steady state at best. So even if those interactions were kind of influencing each other, there would be a robust way of taking care of that. Because I'm applying always this kind of steady state equation. So even if they were transferring onto each other, then the model will be the same. They are treated in the same way.
But don't you think that there are some interactions that actually can influence?
No, but
they can have, different topics may actually have an influence on for instance.
The weights could be different, right? So they could have different trust.
Talk about a war, for instance.
And they may disagree on another topic. In fact, Bernie Sanders disagrees with the role of Republicans. Yeah. Right, so that I would say is a little bit of a pitfall of the model, right? In that case, you will have to, again, cluster based on topics and perhaps apply a different trust matrix, so solve separately these regression problems because you know that the trust that will be placed in some case will be different from the trust that will be placed in another case. But I think this is just the beginning, right? So you can, there is a variety of models. I only mentioned the most popular, right? So here I insisted on the Groot model with stubborn agents. I wanted the stubborn agents to give me identifiability in this steady state condition. But the one model that should be tested, and we are working on this currently, is the polarization model, because that could take care of a phenomena like that. So if you start with opinions that are really different on a topic, you are not going to interact that often, and that's intrinsically captured by the initial opinion difference that you have on the topic. And so that's one of the beauty of the HK model or the Diffusion model, is precisely that it captures that phenomenon that the Groot model doesn't capture. So instead of lumping them in different classes and trying to find the different trust metrics, you could try to find this threshold, which is universal, right, to all of these interactions. It simply describes if you start with the wrong foot, you are never going to converge.
The other question had to do with this. I actually particularly like this analysis about the stubborn agents, and obviously for obvious reasons, obviously, but it seems like one could indeed judiciously place, in a sense, place a stubborn agent to influence. But that also requires, though, for you to judiciously do that, it requires the knowledge of the, your topology, your structure. And
yes,
question,
yes.
have you thought about how you can,
so, but actually,
how you can infer that without necessarily knowing it?
So you can use random graph models, and that's what we did. That's how we created this good performance. Because the best thing is that you achieve some form of expander graph, right? And so in bipartite kind of expander graph, so that you have stubborn agents that roughly talk to the same number of agents, right? And that you can do it at random, but you have to be judicious in looking, in seeking that kind of result. If you just place them a la Erdos-Renyi fashion, then you don't get as good performance in estimation, as good performance in identifying the parameters. But now this is cute. It's not that I'm trying to influence them to do a certain action. Here I'm trying to estimate the parameters. In order to influence them to do the certain action, you have to use the steady state equations. You just use these equations, right? And you need to know D and B to do that. So the other part essentially tells you what D and B are. And after you know that, you try to get the stubborn agents, or you insert the stubborn agents' opinions to lead the other ones to do what you want.
Yeah, but I'm thinking more from a perspective where I do not know necessarily what the network looks like. And I'm thinking of it from a system ID type of
yeah, so that's the knowledge of the network you acquire like this, right? So that's the part where you identify the network, right? So you have placed here, this is your excitation signal. You are purely choosing it to identify the network. You don't care about what these guys are saying. You just want to see the output of that input, right? And there is a placement which is a guideline for the placement which is optimum for that, to give you the best estimate of the parameters. Once you have estimated the parameters, then you can use the same equations to influence them. You see, so you can close the loop at that point. So that's why I think the identification is, in any case, the first step, because the model itself gives you a guideline to how to influence others. But if you don't have the parameters, you don't do it correctly. And so what this says is that you have to place them first to learn the parameter in a strategic way. And then after that, let's use the same exact equations to influence these guys.
I'm still puzzled as to why the tenor of the input, basically of your probe, does not come into the picture. In other words, it's like it's the notion of persistent.
Oh, the excitation. Oh, it comes.
Excitation, right? In system ID, right?
It comes. It comes. But in this case, I'm assuming that these are. So in this case, the way for me, it's more. I'm assuming this is full rank. In any case, right? And my problem is that I have an overdetermined system of equations, so I have to regularize this problem. I have too many variables to identify for the unknowns, and so the guarantees that I've tried to give are more on, making sure that the structure of the problem is not infeasible with relatively few stubborn agents. If I have enough that's full rank, then I have enough equations for the unknowns. But otherwise, it's not just the full rankness of Z that matters. Is that I have somehow some way of describing B and D with essentially low entropy or low order. There was a question from hi, Sasha. Human behavior. So this is actually trying to capture the way human behavior is shaped by others, right? And so that's exactly what these dynamical models are, right? So X is a very simple abstraction, a probabilistic abstraction of your behavior, the fact that you go to the restaurant instead of not going to the restaurant. And what this is, though, trying to capture is the social pressure. The fact that your decision of going to the restaurant is not just based on your experience about that restaurant, but the fact that you somehow incorporate in that decision the behavior you observe from others. So definitely behavior is part of that. But this is mathematics. For instance, there are a lot of more sophisticated notions of behavior, like the cognitive biases that we have, that show that we pay attention more to certain kind of actions rather than others. And under that particular action, that would essentially increase the weight of that information. That would be very interesting to capture in sort of the weight. The fact that these weights actually, depending on the way the agent presents the information, could be much stronger, right? So we know that we are always, violence towards an individual, right, is particularly striking, and we tend to be affected either very negatively or even in some not cases very positively by that, right? Instead, laughter is something that can dispel that kind of attention. So there are all of these phenomena. I haven't personally studied it. I don't know that anybody is trying to put a mechanical, a sort of a simple dynamical model behind it, but it's a very interesting direction.
Capture the erratic behavior of human beings.
Yeah, so there is a lot of studies on cognitive biases. And in fact, the same person that proved that human agents are not rational has an extensive literature. This is studying behavioral economics, right? But that line of study didn't look at social dynamics. He just looked at the behavior of an individual. He carried a number of tests just to see whether the individual was acting rationally or was under the spell of a cognitive bias, but not necessarily the groupthink behavior. But there are very interesting experiments. I mean, this idea of groupthink was by an individual, a psychologist named Ash, that did these interesting experiments where he put people together in a room, and one was obviously a zealot or a stubborn agent that he had inserted, and he showed that people did totally irrational things, completely driven by the behavior of these individuals that were doing stuff that were, obviously non-reasonable.
All right.
Is there more question, or we have to wrap it up?
Are there any questions?
Yeah, one more question.
So I think my question is similar to. Can you push on this thing? Okay.
So, should I push it?
Push it on hold, yeah.
So, question is similar to the previous one, but I think that there is a paper published maybe 1 year ago on Science Review. They said they actually researches heterogeneous networks in the context of the consensus network. So their mapping of the W matrix in your application is actually a nonlinear function. So
well, actually the Diffusion model is nonlinear. The Diffusion model, the polarization, the model for polarization is nonlinear.
So they consider like the sheer behavior kind of function, saying that my current state from the time step of -1 to the mapping to the next state is a nonlinear function. They show that under certain function, the consistent behavior is changeable.
Yeah, but that's exactly what happens. I mean, there are several models of this, but that's exactly this model. This model has exactly that feature. This is a nonlinear function of the states, and that's why it leads to this behavior, right? So that's, there are many other ways you can change that nonlinearity. But if you have this kind of hard behavior, you observe interesting patterns emerge, even if you don't say, okay, there are these people that keep the opinion constant, right? So that's another way of partitioning a matrix, but here is just playing on that function. And by the way, the people that suggested this model looked at a lot of tweaks. I'm just showing you the simplest form of what they look at, but they look at different thresholds, different weighting parameters, and they obviously see more complex behavior as they change these.
All right, more questions. Let's thank our speaker again.
Thank you.